Welcome back. This is the second part of how to build out the Skill Cloud Trader project and implement a client module for interactive brokers. If you haven't watched part 1 where we installed the minimum version of the Skill Cloud Python project, please take a moment to do so. You will need to have the minimum installation set up on your computer to follow along when we continue. All the code in this episode is available for free on our homepage as well. Just move over to skillcloudacademy.com and log in or register. Locate and enroll in the course Skill Cloud Trader Part 2. There you will find the complete Python project folder in the course attachments. Here's the agenda for Part 2. First, we'll take a closer look at the IB API. There are two main options we can choose from, and we'll discuss some pros and cons with both. Then we will download and install the IB Python API along with another application that we need to have running on our computer to make a connection with IB. Next, we will look at how to manage the project in run versus design time. In a runtime environment, the system will run continuously, so it is very important that we can hot load and unload clients. We will take a look at how this works. In design time, however, we can start and stop the whole system inside our IDE, which is more convenient for testing and debugging than hot loading clients. We'll cover this too. Then we will move on to implementing the IB client. We'll talk about how we can use base classes to encapsulate the functionality we need to establish the broker connection so we can reuse this code each time we want to build a new IB client. In the next lesson, we will solve a common real-life problem in automated trading, obtaining historical prices. We will learn how this is done in the asynchronous IB API, and then we will build a wrapper class to make this process synchronous instead. If you have ever tried the third-party IB InSync Python module, you will recognize a lot of what we'll be doing here. This will make our lives a lot easier. Last but not least, we will customize a new dashboard page that communicates with our IB client. We will call the historical data function from the dashboard to display a snapshot of the historical prices for a given period. But let's start with the IB API. IB provides two different integration technologies. One is called the Web API, and in technical terms, this is a common REST API. The other one is known as the Trader Workstation or TWS API, and this is a WebSocket interface. The main difference between these solutions is that the web interface uses what we call synchronous communication while the TWS interface is asynchronous. Now, if you're not used to API programming, this may sound like complete gibberish, but it is actually not that complicated, at least not for our purposes. Let's say we want to retrieve some data with the web interface. Once we are authenticated by the server, we typically use a GET function to ask for the data. Depending on what data we want, we call a certain endpoint on the server side, and this endpoint is defined by the URL that we supply as an argument to the GET function. We typically also supply some additional arguments to limit or filter the data we want. Then our function will wait for the server to return the data before our code execution continues. If we want to do the same thing with the WebSocket interface instead, we need to use two functions. The first function requests data from the server similar to the GET function before, but it does not wait for the data to be returned. In fact, the request function does not return anything at all. So how does that work? Where does the data go? This is where our second function steps in. This is commonly referred to as a callback function, and as the name implies, this function handles a call that we get back from the interface when our requested data is delivered. Once the server gets our data request, it starts serving the data back to us. When our data arrives, the callback function is called, and the data is passed as an argument to the function. This method of integration is called asynchronous because the data request and delivery are separate events. We're going to implement a REST integration in a later tutorial, but for now, we will use the WebSocket API. The primary reason for this has to do with how long we can stay connected without having to re-authenticate our connection. With the REST API, we can only stay connected for 24 hours before we need to log in again, but with the TWS integration, we can stay connected for an entire week. This is quite important for a continuously running service. If we need to log in every day, there's a risk that we will forget, and then the service won't be connected. This can be really bad if a trade needs to be closed quickly. When we use the TWS interface, we cannot connect directly to the IB servers. We need to go through either the Trader Workstation or the IB Gateway. The Trader Workstation is generally not suited for this because it's quite heavy to run. It can be quite useful for testing though, because we can validate what our clients are doing as we mentioned earlier. The IB Gateway is a better choice because we don't need to run the entire user interface. The gateway only contains a simple console where we can see which clients are connected. The great thing is that we can use the same code regardless if we want to go through the workstation or the gateway. This means that we can easily switch between the two if we want to use the workstation for testing and the gateway for live trading. It is important to understand the authentication process when we integrate with an external server. When we use the IB gateway, it will handle the authentication for us. Before we can connect to IB, we need to manually log into the gateway. All this happens on our local machine and behind our firewall, which means that we need no additional authentication to connect our client over our local WebSocket. All we need to specify is the local host IP address and the port number where the gateway is connected. If we zoom out a bit, our setup looks like this. We have our entire system running in our local environment, and then we connect to the external IB server through the IB gateway. Now let's install all the components we need to implement the IB client. We move over to the IB site, and the easiest way to download the IB gateway is probably to search for it in the search bar. Locate the gateway download in the search result and download the install file. Then follow the instructions and install it on your computer. We will install the Trader workstation as well. We will connect to this instead of the gateway in a later tutorial when we automate order execution. The workstation allows us to inspect the orders that we create, which is quite convenient, and we cannot do this in the gateway. Locate the Trader workstation installation file and install it. The last thing we need is the IB Python API, and we can install this directly with pip. Alright, so now we got the environment set up so we can start building our IB client. But before we jump into the Code Studio, let's first have a quick look at how we handle clients in runtime compared to design time. Once our system is running in a live environment, we don't want to start and stop the background service each time we add or change a certain client application. That would disrupt other running clients, and it could lead to unpredictable events like trades failing to open or close in time because the responsible client is stopped. In a live environment, we instead need to use hot loading, which means that we can load and unload clients without stopping the background service. Here's how it works. If we open up the project and move to the client folder, we can make a copy of the test client. The copy is detected by the background service and immediately visible on the dashboard homepage. If we refresh the page, we'll also see the new client in the navbar. If we click on it, we can verify that it is associated with its own dashboard page. We haven't customized this page yet, so it will display the default page. We can change the name of the client copy. When we do this, the background service will stop and unload the copy. It then loads the renamed client and starts it. To change the name that appears in the navbar, we can open a client file and change the display name. For this change to take effect, we need to stop and reload the client. Once we've done this, we can reload the dashboard, and we see that the navbar name has changed as we expected. Now let's change the name again, but this time we add a leading underscore. The client is unloaded because the leading underscore makes the background service interpret it as a base class. We will use this base class to implement the interactive brokers connection. Now we know how we can hot load and unload clients while the background service is running. This is essential because in a live trading environment, we want the background service to run continuously so we don't upset any of the other running clients. But right now, we are in development mode, and it would be more convenient to run the entire system inside our IDE. Then we can have all the code modules easily accessible when we test the code, and we can make use of the debug functionality to track down errors. And there's nothing stopping us from doing this. Both the background service and the Dash web server are very lightweight and starts more or less immediately, so we won't add any significant time overhead even if we test the code very frequently. To start the system, we simply run the service.py module inside VS Code. Now we understand how to hot load clients in production and how we can also start and stop the entire system from inside the IDE. It's time to start implementing the IB base client. But why do we need another base class? Well, there are two main reasons. First, we expect to develop several IB clients, and they will all need to implement the same code to establish the broker connection. If we put this code in a base class, we can reuse it for all IB clients. Second, putting the code in a base class means we can maintain it in a single spot rather than having it scattered across many different clients. First, we must import the base client so our IB client can be loaded and started by the background service. To make a connection and start communicating with IB, we need to import the client and the wrapper modules from the IB API. The config module contains a number of static settings, including the host and port number that we need to connect to the IB gateway. We will also import the threading and time modules. Our IB-based client needs to inherit the eWrapper and eClient classes from the corresponding modules in addition to the client base class. Then we need to call the init constructor method of the eClient class. The display name is not used for base clients, but we can change it anyway for clarity. Next, we implement a new method to connect with IB. First, we call the connect method that we inherited from the eClient parent class. We need 3 arguments to do this. We already imported the host and port details from the config file, but we also have to pass on a client ID. This ID is generated by the background services and passed to the client constructor when the client object was created. Then we call the run method. Note that we execute this method in a new thread. The reason for this is that the run method will start an infinite message loop that sends and receives messages over the WebSocket connection. If we don't do this in a separate thread, our client will be stuck, hanging inside the message loop. The run client method is already defined in the client base class, but we will override it here and include the call to the connect to broker method. This means that when the client is started, it will contain 2 threads running in parallel. The client's internal main loop where we can schedule our own tasks, and the IB connection through which we communicate with interactive brokers through the IB gateway. Finally, we will override the main loop method in the client base class as well. We want to make sure that our IB client is connected at all times. If the client is disconnected for some reason, the main loop should pause until the connection is re-established. We add another loop to implement this logic. If the client becomes disconnected, a reconnect will be attempted every 5 seconds. We will revisit this later and add some timeout and alert functionality, but for now, this is good enough. The main loop in the base class calls the scheduler to execute any pending job every second, and now that we override the main loop, we need to add that call here as well. Finally, if the stop flag is raised, we exit the main loop and disconnect from the broker. Let's take a look at what we got so far. In the introduction course, we introduced the client base class containing the basic interface that allows it to be loaded and controlled by the background service. We just implemented the IB base class that extends the client base and allows the client to connect with IB. Now we want to combine these 2 interfaces into a single test client. If you are not used to object-oriented programming, you might think that we need to include both these base classes in our test client, but that's actually not the case. The IB base class already inherits all the functionality from the client base class, so everything we need to connect with the background service is represented in the IB base class as well. All we need to do is to import the IB base client module and use this to create our test client. Let's move over to the Code Studio and create a new Python file called IB test client. Here we can create a fully functional IB client with just 5 lines of code. We begin by importing the IB base client that we just implemented. Then we create a new client class that inherits the IB base and initiates it. We set the client name so we can identify it in the dashboard navbar, and that's it. We're ready to go. But before we start the system, we need to start and log into the IB gateway so we can connect to interactive brokers. We will log into our paper trading account, and after a couple of seconds, we will see the IB gateway console window. Back in the Code Studio, we select and run the service.py module to start the background service in the debugger. If we go back to the Gateway console, we now see that an API client is connected, and if we move over to the dashboard, we can also see that our small IB test client is running. We can also see that it is connected to the IB gateway. If we close the IB gateway to simulate a disconnect, the connect status in the dashboard will change to false. In the Code Studio terminal, we see that the client is trying to reconnect to the gateway. If we start the gateway again, we can verify that the client successfully reconnects again. Now we can connect with interactive brokers, and we got some basic functionality in place to manage disconnects. In the next lesson, we will take a closer look at how we can download historical price data from the IB Market Data Server. As we mentioned earlier, this becomes a slightly complicated process with the IB API because of the asynchronous interface design. To make life a bit easier for us in the future, we will also implement a synchronous wrapper function that makes downloading prices a lot more straightforward. We begin with creating a new Python file and name it IB client. Then we import the IB base client just like we did before, but to download historical data, we also need to import the contract module from the API. We also import the pandas and time modules. Just like before, we also define our client class and set up the constructor with the display name and two new properties called historical data and historical data end. The leading underscore signals that these properties are internal to the class and not intended to be manipulated from outside. We also schedule a new job to run every 5 seconds, and we will define this job a little later. Then we define our wrapper method for downloading historical prices. This method will wrap the asynchronous API calls and expose a neat synchronous method for historical data. Next, we call the request method for historical prices in the API. As we discussed before, this function will not return any data, and once the request is made, the program execution will just continue. We use the Korg syntax to receive and pass on an arbitrary number of keyword arguments from the wrapper method to the request method. Then we trap the program execution in a while loop that runs until all historical prices have been delivered. When we reach the end of the price stream, the historical data end flag will be set, and we will implement that in a second. We use the sleep function to check the end flag twice every second. The historical data method is a predefined callback function that will be called from the API each time we receive a new price from the stream. Contrary to the IB REST API that we also talked about before, the IB WebSocket interface won't deliver all the price data in a chunk. Instead, each price bar will be sent individually. The price bars in turn contain the open, high, low, and close prices, and we need to resolve this to build a data frame that we can use for analysis. We extract these as properties from the bar object and put them in a list that we then append to the historical data property that we defined in the constructor. This means that we will end up with a list of lists when we collect the bar data, and the reason for this is that this structure converts easily into a pandas data frame when we are done. Next, we implement the historical data end callback. This method is called from the API to signal that the last bar has been delivered. We use this to set the historical data end property to true, and this will make our wrapper function break out of the waiting loop. We move back to the wrapper function and reset the historical data end flag so we are ready for the next call and convert the price data from a list of lists to a pandas data frame. Finally, we flush the historical data property and return the data frame from the wrapper function. To test our new synchronous method, we define the job that we scheduled above in the constructor. To download historical data, we need to create and pass a valid contract object to the request method. Here, we will use the Apple stock contract, and to uniquely define this contract, we set a few properties. Depending on what type of contract we want, the required properties may be different, but we can use the documentation to determine what's needed for a particular contract type. Then we call our new method, and there's a whole heap of arguments we need to provide to keep the underlying request function satisfied. Remember that we use the Korg syntax to just relay the arguments from the wrapper to the API function, so we should specify them according to the documentation for the rec historical data function. We will get back to this, but first we will test the wrapper function. We complete the job by printing the return price data frame to the terminal window. We make sure that the IB gateway is running and start the background service. After a few seconds, the requested data frame is printed. Alright, so the wrapper function works as we expected, but let's see if we can improve the code a bit. First, there's a number of arguments that we rarely care about, and we can use default values to avoid having to set those each time we call the wrapper. In Python, we could set defaults directly in the arguments list in our wrapper, but then we would lose the flexibility of the Korgs pattern. Instead, we will simply check whether an argument is set in the Korgs dictionary, and if it isn't, we will set it to a default value. That makes our wrapper look a bit better. We got basically the same situation for the contract data. For a stock contract, we typically just want to define the symbol. We can simplify this by introducing a function that takes the symbol as an argument and sets all the other properties as defaults. We will create a new module for this function because we will most likely implement more of them for other IB data objects further on. We call the module IBUtils and define a function that will return a US stock contract. Back in the IB client, we now need to replace the contract module with IBUtils. Okay, so now it looks a lot better. We can use the wrapper to fetch historical data for a stock contract with a straightforward synchronous function call and a minimal set of arguments. But there is still one last thing we can improve. When we start implementing trading strategies, we may want to use our wrapper method in multiple clients. Wouldn't it make sense to centralize this code just like we've done before in a base class? Well, this is very easy to achieve. We rename the module to IB client wrapper with a leading underscore so the background server understands that it's a base class. We don't need the utils module anymore, so we can remove it. We rename the class to IB client wrapper and change the display name, although it's currently not used for base classes. Then we remove the job scheduling, and finally we remove the job itself. We create a new IB client file in the project. Now we can rewrite the IB client, but this time we derive it from the IB client wrapper instead of the IB client base. We also need to the utility function, so we can construct the contract object. We put the job scheduler and the job itself back in, and that's it. Now we can create client that fetches historical prices with only a few lines of code. Let's return to our evolving class hierarchy and recap the different levels. At the top we have the client base. Here we implemented all the code that is necessary for docking with the background service. Then we have the IB client base that extends the client base. This is where we keep all the code to establish and maintain a connection with interactive brokers. Next we have the IB client wrapper extending the IB client base. Here we implement the wrapper functions that transform the asynchronous call structure in the IB API into a synchronous interface. This base class will grow substantially over time when we implement new wrapper functions for additional data objects as we proceed. Finally, we have the live client that inherits all of the above through the IB client wrapper. Ideally, the live client should only contain code specific to its task. It should contain the job scheduler and the job itself. The job could be any specific task like executing a particular strategy or compiling a scheduled report. With all this in place, we have a solid foundation for developing the SkillCloud Trader platform without losing control over the codebase. In our final lesson, we will build a web page with Plotly Dash and Python to visualize the historical price data that we downloaded from interactive brokers with the IB client. The Dash framework gives us some very powerful tools to implement advanced web dashboards in pure Python. We will use this to implement a simple candlestick chart on the SkillCloud dashboard. But in case you haven't worked with Dash previously, we will start with a short primer explaining the basic concepts. Let's have a look at a minimal Dash application. Note that this is not part of the SkillCloud Trader, so it's only to illustrate how Dash works. First, we import the Dash class and some other things we'll need from the Dash module. We also need the datetime module in this example. We begin with creating the Dash app, and we can think of this like a local web server. We can connect to it from our browser, and the app will serve the web pages we define back to the browser. To create a web page, we can assign text and web components to the layout property. The Dash framework comes with a vast number of components we can use, from buttons and text fields to more complex components like charts and data tables. In this case, we stack two components on top of each other in the layout, a div component and a button. If you're not used to HTML code, the div is essentially just a content placeholder. The button is a dynamic component that triggers an event when it's clicked. We can capture this event and define a function to perform a certain task when the button is clicked. The standard way of doing this in Dash is to use a special callback decorator. The decorator is used to route the input and output data between the web component and the decorated method. This in turn is done with the input and output objects that we create as arguments to the decorator. When we define the component, we specify an ID property. This property allows us to reference the component from the callback function. In our example, we define a callback that takes its input from a component where the ID equals button, and this is how we link the callback to our button component. The input object also requires a property from the component. In the case of a button, we pass the nClicks property. This is like a counter associated with the button that keeps track of how many times it has been clicked since the page was loaded. We don't really care about this in our case, but we still have to provide a component property to the input object. When the button is clicked, we want to display the current time on the web page. This means that we need to send the current time to the div object. This is done through the output object that works very similar to the input. We set the ID for the div to time field. We use this ID to reference the div component in the output. Then we specify which property of the div object that should receive the value from the callback function. In this case, we set it to children. Children is a special keyword in Dash referring to the first property in any HTML component. With these few lines of code, we now have a fully functional web page. Let's run it and see what happens. When we click the button, we trigger the callback that is linked to it via the input ID. Each time we click the button, the time field updates. This was an all-in-one script solution with a Dash server and the layout code in the same file. That works fine if we're building a small application with a single page, but we want to create something a little bit more structured. We need a multi-page application where we can add new pages as we add new clients. It would be great if each page was defined in its own file and loaded on demand into a main navigation page. There are many different ways to implement this, and there are guidelines in the Dash documentation on what's best practice for multi-page apps. In the SkillCloud dashboard app, we will not follow these guidelines to the letter. Instead, we will implement pages as class objects. There are several reasons for this based on how we share data across the application, etc., but perhaps it's mostly about preferences. Anyway, let's see how we can implement a candlestick chart that requests historical prices from the IB client. We will see how our approach differs a bit from the previous example as we walk through the code. We can connect a specific client module with its own dashboard page by a naming convention. We simply move to the web folder and create a new Python file with the same name as the client, followed by _layout. We begin with importing some things from the Dash module, but this time we won't import the Dash app itself since it's already instantiated in the Dash server module. The candlestick chart that we will display is a web component in the Plotly module. It's already part of the Dash installation, so we can import it directly. We also need the utility function that we implemented before, so we can create a contract object directly from the stock's ticker symbol. Then we create the layout class. When a dashboard page object is created, we pass references to the Dash app and the associated client as arguments to the layout constructor. By doing this, we can share data with both the client that the page belongs to and the Dash app itself. In the previous example, we used the callback decorator when we defined a callback function, but here we register the callback directly with the Dash app. This is just an alternative way of doing it, and in my opinion, this looks a bit cleaner than the callback decorator. Just like before, we use the input and output object to bind the callback to the sending and receiving web components. The only difference is that we also need to provide a specific reference to the callback method, which we didn't have to do with the decorator. When we navigate to a client page, the layout will be requested from the getLayout method. In this case, the layout that we return consists of a graph object that we can use to display our candlestick chart. But there's one little twist, and that's the loading component that wraps the graph. This will show a loading spinner when the graph is being updated. Next, we implement the callback function that updates the graph with data from the IB client. We use the getHistoricalData method that we just implemented to fetch the time series of prices from the IB client. Then we use the Plotly graph object to construct the chart and return it. The return object is then routed to the figure property of the historical data chart component as we defined it in the output object. But how is the callback triggered in the first place? In the previous example, we clicked a button to update the output, but now we don't have a button. In the input object, we have defined the chart itself as the triggering component. What's going on? The way it works is that all callbacks will be fired by default when the page is loaded unless we specifically suppress this behavior. In this case, it works to our advantage, so we use this call to load the chart without any other components involved. Now that we call the getHistoricalData method from the dashboard page, we don't need the job we defined in the IB client, so we will do a little housekeeping and comment that out. Let's run the service and have a look at our chart. The IB client page shows up in the navigation bar, and if we go to the page, we can see the candlestick chart. This is all fine, but if we start to abuse the page, we will soon find out that it is quite fragile. For instance, if we hit the reload button repeatedly while the chart is loading, the page will hang. This is not acceptable, of course, and whenever we implement user interfaces, we need to really stress test them to make sure they are stable even when a user does things we didn't intend or expect. It's time to wrap up this session, but please stay tuned for the next episode. Then we will continue to build out the SkillCloud Trader with an email module, and we will expand the IB client with a trading strategy. We will set up the background service in the Windows Task Scheduler and revisit the dashboard layout. So a lot of interesting stuff coming up. As always, if you found this video useful, please take a moment to like and subscribe. This is really important to us. Thanks for watching and see you again soon.